Thank you, sir, and thank you all for being here for this presentation. First of all, I would like to draw your attention on this very first slide. That is basically mentioning some keywords I have been thinking about for over the last 5 or 6 years. This is the title of my PhD dissertation, Numerical Simulation, Nonlinear Analysis and Control of Bio-Inspired Flows, a Step Towards Autonomous Vehicles. So this is how I would proceed with this presentation. First of all, I would mention what motivated me for this study, and a brief introduction about my numerical methodology, research methodology which I have employed for this research. Then I would move on to different parts, different research phases you can say. Part 1, which is about rigid body aerodynamics, then flexible body aerodynamics, and then we developed some reduced order models. And finally, I would move on to the conclusions, a few contributions which I made during this research, and finally the future recommendation would be presented. So ladies and gentlemen, most of the time, inventions and discoveries, we take inspiration from natural systems. So these are, you can say in case of micro air vehicles or micro swimming robots, same inspiration comes into play. You can see few applications over there. Those applications have been designed both for military and civil purpose. And to design the optimized, you can say, to propose optimized and efficient designs, this is a challenging task because so many subsystems are involved, so many disciplines are involved. Most particularly, I would try to have your attention on this particular figure where you can see multiple bodies fishing in some group. This is known as fish school, and by the way, what they are doing, I would explain it later on. They are trying to control the flow around them. They are taking advantage of each other. These are the examples of few heavily funded projects. The first one, DARPA's initiative. This is Defense Advanced Research Project Agency in USA. In 1990s, they initiated this project where they intend to develop few micro and nano air vehicles. You can see one example over there. Still, it is just a prototype. They haven't manufactured it properly. The second one you can see in this figure, the lower one. This is about MIT's autonomous underwater vehicle. It is still under development. And then a very recent project is being done by a consortium of different universities in USA, and that is titled by Bio-Inspired Flexible Propulsion for Fast, Efficient Swimming, but physics are we missing. This is being done by Dr. Haipo Dong as well, and I was fortunate enough to have a place in that group for 6 months during my stay abroad. Now, whenever we talk about natural systems and we are talking about flying, it involves complex fluid structure interaction phenomena. So, because we are taking inspiration from nature, these flows are known as bio-inspired flows. And if we are performing numerical simulations to look at those phenomena, there are 3 ways to model the FSI. One, very first, you give a mathematical function to forcefully move the structure. The second, some degrees of freedom of the motion are controlled by the mathematical function explicitly defined, and few are basically computed through the feedback from the fluid. And the third involves the complete passive motion. So you can say that the third one is the most difficult because it needs two-way coupling. As far as the advantages of this kind of motion is concerned, in nature you see these flapping and undulating motions in case of fishes. The advantage is that most of the time these species operate at low speed flows, and the second advantage is that through this motion they simultaneously produce lift and thrust. So that is why nature adopts this mechanism for production of aerodynamic or hydrodynamic forces. If you look at the flow structures around these bodies, you see that there are complex flow patterns. These complex flow patterns are known as vortices. This is a simple example of those vortices in the above figure. In the first figure, you can see that there is a blunt body, a flat plate put in the flow, and you see certain rotating flows in the downstream direction. These structures are von Karman speed vortices. and they are drag producing. If you look at the lower body, this is a streamlined body. You can see it's a two-dimensional view of a wing or a fin. This is producing exactly reverse of that. For example, if you see the above figure, you have clockwise rotating vortices in the upper row, but in the lower figure, you would have clockwise rotating vortices in the lower row. So the effect would be reversed as well. The lower pattern is responsible for producing thrust. Now, if we focus onto this figure, this is a representative schematic for a natural species. You look at this point, the motion of this point all along its flapping, you will see it is making a figure of 8. That mostly happens for natural species. So if we look at its two-dimensional point of view, it looks like this. So if we decompose the complete motion of the wing into its elementary components, this is the one which is plunging, and this is the other one which is known as pitching. So most of the species employ this kind of motion for producing lift and thrust. And the combination of all these motions is known as flapping. So you can say that this figure provided me with a lead towards my study. So first research question which came into my mind, that what is the contribution of different kinematics towards the production of lift and thrust. So this is the first research objective. When the second comes in, you see that if we look at this plane where both tail and fin are involved, I am just talking about the plane represented as number 2. You see these are the top views. And these tails and fins also perform similar kind of motion, flapping. If you look at this video, that is the undulatory motion of a fish. So this provides me with a second question, that what is the difference? Why fish go for undulatory motion and why the birds go for the flapping motion? So what is the fundamental difference between those two those two motion types? So based upon my literature survey, these are the research objectives which I came up with. First, to quantify the contribution of plunging and pitching motion of a rigid wing fin by finding an equivalence between them. It means this is just a way to look at the equivalence between them. This is just a way to look at the contribution both of these motions have towards the production of aerodynamic lift and thrust. The second objective is that I need to look at the difference between the undulating motion and the flapping motion. And the second thing is that I need to look at the passive flow control technique adopted by different fish while they are moving in a fish school. Looking at those things, I also did some mathematical work as well. I developed nonlinear reduced order models for aerodynamic lift of rigid oscillating wings. So these are 3, you can say, parts of my research. In first part, I am just talking about aerodynamics of rigid airfoils, and the major thing would be contribution of kinematics towards force generation. The second part is composed of undulatory flexible fish, where I added flexibility into the rigid airfoil, and the major purpose is to look at the flow control through fish schooling. And the third part would be the reduced order modeling, which is basically a predictive tool, and it gives us some advantage over the other techniques, the experimental one and the CFDs. So this is about research methodology which I employed for doing this research. This is computational fluid dynamics tool. I use 2 softwares. Basically, the first one is the ANSYS Fluent, and in ANSYS Fluent I use dynamic meshing technique and sliding mesh technique. Both of these techniques, they have their own advantages. And then during my stay at UVA, University of Virginia, I used immersed boundary method code, which was developed by Dr. Haibo Dong. So as far as the nonlinear analysis is concerned, I use the modern tools to look at the behavior, nonlinear characteristics of these flows. The first tool, temporal analysis, you can see many features from these plots. Then the Fourier analysis to look at the spectra. Then phase portraits and point carry maps to look at the period of the solution. And then higher order spectral analysis I perform to look at the frequencies interacting with each other to produce new frequency components. So if we look at any natural system, if we try to mathematically model it, it is always composed of nonlinear complex partial differential equations. So this is well-known continuity equation. In the first equation, this is law of conservation of mass. The second one is the Navier-Stokes equation. This is law of conservation of momentum. And as far as the assumptions are concerned for this study, I choose to talk about laminar flows because I need to perform the nonlinear analysis, so I did not basically want to incorporate the numerical dissipation added by the turbulence models. And the second thing is, I added viscosity into it. So because low Reynolds number flows are viscous in nature. So these forces are very much dominant into it. If we look at the similarity parameters used for the experimentation, this unsteady aerodynamics is based upon Hall number, reduced frequency, and the Reynolds number. If you look at this one, F is forcing frequency by which the wing is flapping or undulating, and we have A, which is wake width. Most of the time it is described as the displacement covered by the trailing edge of the airfoil. And then I have reduced frequency. This is a non-dimensional frequency, by the way. We just multiply this 2 pi f angular frequency with c, which is the chord length. You can see this is the chord length of the airfoil, and it is being divided by u infinity. You can also see the Reynolds number. It is a ratio of the viscous forces and the inertial forces. So at hand we have low Reynolds number flow. I am talking about low speed flows. Now this is the model. This is the mathematical model which I used for the first study for the motion of the airfoil. This is the domain, O-type domain. On the left hand side you can see it is the velocity inlet. On the right hand side you can see it is the pressure outlet. So if we are talking about both plunging and pitching, they have got a phase difference of 90 degrees. These are the schematics of those profiles. Now this is just a flow chart for CFD ANSYS fluid which I used. I meshed the flow domain in Gambit, and then I moved on to Fluent, where I defined the motion as a user-defined function. Now this is a schematic for sliding mesh technique. This is the inner domain, which is basically pitching, and this is the outer domain which remains fixed. You can see there is a non-conformal sliding interface between them. The outer side is the static zone, the inner side is the rotating zone or the pitching zone. On this side we have time varying velocity, and this time varying velocity is equal to the negative of the leaving velocity. And then we added a source term into it to look at the relative motion between the airfoil and the surrounding mesh. And then outside we have pressure outlet. So what is the advantage of the sliding mesh technique is that it allows the use of higher order numerical scheme, the second order temporal scheme in Fluent. And the major advantage is that mesh quality remains the same. It is not going to be disturbed. These are few validation studies. I selected well-known journal studies for the validation. These both include experimental and the numerical data. This is just a representative mesh of IBM, immersed boundary method, which I used at UVA. This is Cartesian mesh, you can say, and IBM is specifically designed for fluid structure interaction problems, but the problem with this method is it can only be used for low speed flows. Again, I also performed validation for that code. I used numerical data and the experimental data as well, although it was already validated by the professor, but still I validated it to keep the setting correct. Now I would move on to the first part of my presentation, first part of my research, that is aerodynamics of rigid airfoils, and this is about the contribution of the kinematics towards force generation. You can see that these are the two elementary motions. This is pitching and this is plunging. We need to see what kind of equivalence can be set between them. Like for example, if we look at the literature, the previous criteria to set the equivalence between them is based upon the effective angle of attack. And effective angle of attack criterion uses this motion of the leading edge, while we use the motion of the trailing edge. Why? Because in one of the papers, Dr. Young from UNSW, he mentioned that actual bluntness in this kind of motion is provided by the motion of the trailing edge. So keeping his comments in view, we went for this kind of equivalence, and we come up with this equals to all number criteria, where we set this total displacement of the trailing edge equal to each other. And these are the results. You can see that these black lines are showing the results for plunging. This red line is showing the results for pitching airfoil, which is from our criteria. And then we have pitching from the effective angle of attack criteria. You can see that the pitching profile from our criteria is closer to the plunging one, and the error of the previously proposed criteria is greater. If you come up to the thrust, it is almost equal to each other. Our criteria performs much better than the previous one. And the major strength of this criteria is that it does not only capture the temporal profiles with low error, but it also captures the harmonics as well. So you can say dynamic properties are conserved. This is a qualitative analysis between the similarity of flows in both the cases. You can see that overall profile remains the same. Now, this is the most interesting one. If we keep increasing the screw hole number, what you see is that this is the typical von Karman vortex field that is being produced by the symmetric motion of this airfoil. Now, if we look at the symmetric motion of the airfoil at a higher screw hole number, either we are increasing the frequency or we are increasing the amplitude of the motion, you see that this wave started deflecting towards one side. So it may go upward, it may go downward. This is known as wave deflection. Now, this looks non-intuitive because it is being produced by a symmetric motion of the airfoil. And there is something which is a nonlinear instability comes into play which drags this whole wave towards one side. And this direction of the wave deflection is dependent on many factors. So what this does is, it basically adds some time average component in the lift. So you can say that the body would start experiencing non-zero time average lift component. Now this is associated with this second harmonic. If we look at the spectra, this is for low screw hole number flow. This lift spectra is being shown in this figure. You can see that Cl2 is quite small. But if we increase the screw hole number, you see that the strength of Cl2 has been increased. It means that this wave deflection is associated with increased strength of Cl2. So we can say that basically, looking at the other figures, this is the profile for time average Cl with respect to screw hole number. You see it is basically, it remains constant at first and then it would start increasing. And similar is the case for the non-dimensional Cl2, and it is being normalized by Cl1. So we have the same kind of profile. So what we come up with, that the wave deflection is being governed by the quadratic nonlinearity, that we measured that quadratic nonlinearity as the amplitude of Cl2. Now these results has already been published in Journal of Aerospace Engineering. Now a simple question can be, what happens if we keep increasing the screw hole number? There is a wave deflection, no doubt at all, but then there comes the point where it all looks random. So this random vortex structure creates random lift or thrust forces, and those can't be controlled easily. So what we need to do is, we need to look at the nonlinear characteristics of this flow. So I have performed that nonlinear analysis through phase maps and point carry maps. At the first place, you can see that there are two loops in the phase map of Cl and Ct. If we plot Cl and Ct against each other, we have two loops. It means Ct is being driven by double the frequency of Cl, and the same is the case for slightly higher screw hole number 0.32. If you look at the point carry map, you just have one dot over there. It means that we have period 1 solution here. And if you look at the screw hole number over there as well, again it is basically period 1 solution. It is, you can say, a verification of the drag puller as well, where Ct is proportional to Cl square. You keep increasing the screw hole number and you would say that the response type would change. You would experience certain kind of subharmonics in the lift spectra and in the drag spectra as well. If we look at the phase map, you can see that there are 4 loops. If we look at the point carry maps, there are 4 dots. So it means period 4 solution is being observed in the system. Now, this is for screw hole 0.36. We increase the screw hole number, and you see that it looks quite random or complex. But by the way, it is not chaotic. Why? Because whenever we plot its point carry map, you see a closed loop. So this is basically an indication of presence of the quasi-periodic solution. And then keep increasing the screw hole number, and this is completely chaos. Broadband spectra, then you have random arrangement of the loops in phase map, and you have random arrangement of the dots in point carry maps. So what we conclude is that this system, this nonlinear system, comes to chaos due to quasi-periodicity loop. And to look at the interaction between different frequency components to produce the subharmonics and the other superharmonics, I have plotted this cross-pi spectrum. This cross-pi spectrum basically gives us a measure between for the interaction between two frequencies. If you look at this color code, it gives us the magnitude of the bispectrum over there. Now, if you look at these frequencies, these are describing frequency 1 on this scale and forcing frequency on this scale. So both are equal, by the way. So we can say that forcing frequency interact with itself to produce double the frequency in drag spectra. This is known as cross-pi spectrum. And if we keep increasing the screw hole number, we would see that there are other components coming into this system. and it is showing that some frequencies interact with each other to produce chaos. But major interaction comes when we talk about the trispectral analysis. Trispectral analysis gives us indication about the interaction between three frequencies. You can see that at lowest two-hall number in figure 8, you do not see much interaction between many frequencies. Although the level is good, it is getting a 25 value. And if you look at the highest two-hall number, more and more frequencies starts appearing on this plot. You can see that. So it means this cubic coupling is stronger to produce the chaos in case of this nonlinear system. We have already presented this result in the AIAA conference last year. Now I would move on to the next part. Here in this next part, what I added is I added the flexibility into this rigid airfoil. So due to this flexibility, I am talking about the example of the undulating flexible fish. First, I would talk about the difference between the undulation and flapping. These are few examples. You can see I have already shown you this video. This is basically traveling wave motion of the fish. I have taken the example of the saty fish, which is usually found in Atlantic Ocean, and this is the motion of the airfoil. You can see it is being modeled as an Akhtar 0012 airfoil, and the motion is provided at the chord of the airfoil, which is acting as the spine of this fish. Again, we can talk about the two-way coupling, but in this case, I am providing the actual motion profile, which was calculated by the biologist, and it is available in the literature for the undulatory motion of this fish. Now, these are few schematics. This figure represents the maximum amplitude of undulation at different points along the fish length. This is the complete envelope of the motion of the spine of the fish. These are the mathematical relations by which we modeled it. By the way, this A0, A1 and A2, they are computed by the boundary conditions available in the literature. I have done that. And this is the representative schematic of the grid. I use this kind of grid. This is Cartesian, and you can see that those two fishes are there. We can also do it. We also did that for a single fish. Now these are vorticity contours. If you see at the lowest two-hall number, those vortex pattern looks like bone carbon vortex field. As we increase the two-hall number, they become parallel to each other, and as we keep increasing the two-hall number, we started experiencing some kind of reverse bone carbon streak. So what is the difference over there is that we do not experience any kind of wave deflection over there. So this is difference. And then what vortices tend to dissipate after covering a longer distance from the fish at highest two-hall number. In the previous literature, it was mentioned that if fish undulates with higher frequency, those vortices would tend to dissipate after covering a smaller distance from the in the downstream direction. But these results are new. You can say vortices get stronger and stronger. Now this is the figure. If you remember, I just show you this figure again. This is for wave deflection, and this is for undulatory motion in case of for the swimming fish. You see that although the two-hall number remains the same, but in this case we do not observe any kind of wave deflection. In this case we are observing some kind of wave deflection. So you can say that the nonlinear instability which is over there, that was not experienced in this case, and most you can say most probably that would be the fixed force bifurcation which comes into play to bring that wave deflection into the system. Now why is it practically important? The practically important thing is that if we are talking about the wave deflection, it gives some kind of non-zero time average value of the lift on the structure. So it means you need to add a control surface at all the time if you are implying flapping wing for designing of autonomous vehicles. What you can do is you can change the motion form and you can avoid that kind of time average value. Now I would come on to this part where I am talking about the flow control through fish schooling. Here you can say we have put two fish in Titan configuration, and this first fish is undulating with more frequency, with greater frequency. The second fish is undulating with lesser frequency. Why is it so? Because in fish schooling, you would always see that the follower fish, the real fish, that undulates with reduced muscle activity. So frequency is smaller. Now, if you look at the spectra, you can't see anything, or you can't quantify anything from the temporal profile. So you need to go for the drag and lift spectra. This upper spectra is for undulatory fish, which is over there, the upstream one, the leader one. You see this F1 is representing the undulatory motion of this fish, but you see a very small component a very, you can say, small amplitude or F2 frequency in its spectra. So it means this fish is not being affected by the frequency of this one, and you would see that profiles in the time average or drag coefficients as well. If you look at the lift spectra of the rear fish, you would see that the dominant component of F1 is present over there. So it means the follower fish is being affected by the leader fish. And the same is the case for these drag spectra. You can see the drag spectra of the upstream fish, you can see the drag spectra of the downstream fish, and you can see different frequencies are interacting with each other. So that is where bispectrum helps us to quantify the interaction level between these two frequencies. So these are the profiles for time average drag. You can see even if we keep decreasing the frequency of the the rear fish, no effect was felt by the upstream fish. But if you look at the drag spectra, the time average drag coefficient of the rear fish, you can see that it takes advantage under certain conditions. Now this is quite interesting, these 3 points. These 3 points are quite interesting. Why? Because although it is moving with low frequency, but still it manages to get the same drag coefficient. So both the fish are trying to have the same velocity, even if the lower fish is moving with the reduced muscle activity or with the reduced undulating frequency. You can see that there is a very less percentage difference between the drag coefficients of both the fish. So you can say that if this rear fish is getting advantage of the upstream fish, it is known as drafting, and if the upstream fish is taking advantage of the rear fish, it is known as inverse drafting. So you can say inverse drafting would be observed in all the cases, but drafting would be observed in some cases. So that is why fishes maintain a certain distance between them once they try to undulate. The question is, why does it only happen at certain points? So I try to answer that question over there. If you look at these profiles, you see that if we keep decreasing the frequency of this rear fish, you see that the wake width is increasing. So if the wake width is increasing, it induces more pressure drag onto this fish. So that is why, due to this expanding wake, this fish starts experiencing more drag even if its frequency is going to the lower side. What happens to the upstream fish? It takes advantage of the inverse drafting due to wake splitting. What wake splitting does is that the rear fish, it just split the wake in the wake of in the downstream direction of the upstream fish. So what happens is its pressure increases. So because its pressure increases, you can see it adds more lesser pressure drag onto the upstream fish. So this is already there. We are to submit the revised manuscript. The final one, we have already received the positive comments into it from Journal of Fluids and Structures. Now, I am looking at the quadratic coupling. I have already shown that there are frequency interaction between the drag spectra of the rear fish. If you look at the bispectrum values, you see some higher magnitudes at different frequencies. So these frequencies say that we need to look at the symmetry of the wake modes or the nature of the wake modes which are being developed by these frequencies interaction. I adopted the methodology described by these papers in the literature. We put certain probes in the downstream direction of the fish. You can see I have computed different amplitudes of the harmonic components from the Fourier spectra. Then from Fourier spectra, I can decompose the velocity signal into its odd part and its even part. And then from the odd part and the even part, you can compute the energy levels, which is known as, basically we are representing it as O for the odd energy and this is E for the even parts energy. If the ratio between them, O by E, is greater than 1, it means odd mode is dominant. If the ratio is lesser than 1, it means even mode is dominant. If you look at these plots, these are representing phase plots and amplitude plots for different frequencies. For different frequencies, you can see that if you move in the vertical direction, these are the profiles of original velocity signals and its even and odd components. In this figure, for frequency F1, which is the actual forcing frequency of the fish, you can see that the odd frequency component is dominant. It means that hydrodynamically this is an anti-symmetric mode. If you look at 2F1, this 2F1 is being generated by F1 frequency with itself. So that is why it needs to be reversed, because according to symmetry principles, those two anti-symmetric modes should be combined together to produce a symmetric component. So this is symmetric. Why? Because you can see that the even component is almost equal to the original one and the odd strength is very small. If we look at the 3F1 component, this 3F1 component is being produced by the interaction between F1 and F2. So F1 is an anti-symmetric mode, 2F1 is a symmetric mode, so it means due to their combination an anti-symmetric mode should be produced at 3F1. So this is the case which can be seen also in this figure. And the interesting thing is that the symmetry principles which have been defined for club bodies earlier in case of circular cylinder or oscillating circular cylinder, they are also true for streamlined bodies. So you can say that this is a similarity found in the nature of all these kind of flows, although the body type is completely different. These are the ratios for different screw-valve numbers at different frequencies for the single phase. Now we are preparing its draft and inshallah it will be submitted very soon. Now this is the last part of the research. I am talking about the reduced order modeling. Once we talk about the nonlinear features of both of these airfoils, the rigid one and the flexible one, I talk about the mathematical modeling for the lift force produced by these airfoils. So I did that through a Van der Waals oscillator model, a well-known model in nonlinear mechanics. I developed that model for pitching airfoil, plunging airfoil and flapping airfoil. So you can see that one model would be applicable to all. Why we need to develop the reduced order model? Because we have experimental techniques which can be costly enough. We have CFD techniques which can be very time consuming, so we need to go for some simple approaches. So this simple approach is a reduced order model. That reduced order model can be composed of a simple ordinary differential equation like the one which I am going to present over there. And this is based upon self-excited oscillators. We can model one dynamical state of the system using these models. This is known as phenomenological approach. And then we have a direct approach as well, where we can talk about the computation of reduced physics for model reduction, and POD, proper orthogonal decomposition, is a famous example. To go for that reduced order model through an oscillator, you need to first prove that a limit cycle exists. This is basically, you can see in this figure, I am trying to show you the plots between CL and CL dot and CL and CT at different screw-valve numbers. Now I have adopted different initial conditions, and you can say that for all the initial conditions, the solution is attracted towards the same side. Solution is attracted towards the same, you can say, contour or same attractor. So this happens in both the cases, and this is also for CLCT. We have already observed this is quite natural. So after proving that there exists a limit cycle, we modeled the lift of the airfoil through this Van der Waals oscillator model. And what I introduced is, because of this appearance of this CL2, and the CL2 is important due to the wave deflection at high screw-valve number, we modeled the behavior of this quadratic nonlinearity through alpha CL CL dot. So this can be computed through CL square, this can be computed through CL dot square, this can be computed through CL CL dot. So choice is made based upon the phase between the two components. So I did that through alpha CL CL dot. And this is the cubic damping, this is the forcing term. I used the perturbation technique, a well-known method of multiple scales. The advantage of that method of multiple scales is that you assume different time scales. You can assume the fastest time scale, T0 equals T, which is representing seconds. You can say this is the slower time scale and this is the slowest time scale, which sort of represents hours. Considering the primary resonance, why? Because vortex shedding frequency is exactly equal to the forcing frequency. The excitation force is being modeled using a cosine function, and in case of method of multiple scales, the first order derivative and the second order derivative, they are defined like this. The assumed solution for CLT, to apply this perturbation technique, we have a second order solution, CL0 plus epsilon CL1 plus epsilon square CL2. This epsilon is just a bookkeeping term. Now, there are some problems with the previous model, that although it captures the time and the spectral history very well, it gives singularity at eta is equal to pi by 2. Eta is the phase difference between the forcing and the CL. And it also involves a very small amplitude of the forcing amplitude. And then we also need to model the time average component of the lift force, which the previous model was not able to do that. So what I did was I changed the quadratic nonlinearity through alpha CL square. So although it looks non-physical, why? Because it is not following the phase difference between CL and CL dot, but still, just to model that time average component, we brought that into the system. And you can see that its solution through the perturbation technique gives us a time average component which is dependent on A naught. So this A naught is the DC component of the lift, time average component. This shows trend of linear damping and the non-linear damping. You can see that quite interestingly, although these three motion types are completely different, but at some Stru-Hall number, they start approaching each other. So quadratic nonlinearity, the magnitude of the quadratic damping remain the same for Stru-Hall numbers after a critical value, and the same is true for the stabilizing cubic damping. Now these are the models which we get for all the damping types and CL bar by comparing this reduced order model, analytical model, and the CFD solutions. So this is the advantage. You can model CL bar through the ROM, and you don't need to go for the complete CFD. So what we have done is we have developed a database, and it can only be used to solving an ordinary differential equation. And this is also under preparation. The strength of the previous reduced order model that can be described by applying it onto the other structures. So as an example, we applied the same model towards the top of the wind turbine. So those results are already published in Journal of Computation and Nonlinear Dynamics. So this is the model. You can see that this is the same model which we use for tau dot. Now this time it is, the previous one used CL dot, so now we are talking about tau. So this is tau dot, and this is the analytical solution. Now coming on to the contributions. In this doctoral research, I developed equivalence between pitching and plunging motion. This is a significant improvement from the previously proposed criterion. And then we compared undulatory and the flapping motion, and we come up with the conclusion that no wave deflection is observed for undulatory motions, and this is quite important for the design of autonomous air vehicles. And then this is the third one is we quantified the drafting and inverse drafting for the fish undulating asynchronously in tandem configuration. This is again quite important if we are talking about multiple AUVs. So forward fish can go with the reduced frequency. So this can save the energy. And finally, I developed reduced order models by introducing the quadratic nonlinearity. So this helps us look at the model, look at the wave deflection as well. Coming on to the conclusions of my doctoral research. First of all, I identified the role of the airfoil's trailing edge kinematics for plunging equivalent pitching amplitude, and developed the equivalence criteria, which is better than the previous one for the lift as well and for most the thrust. And then I established that the quadratic nonlinearity is the governing factor for wave deflection phenomena. I established that route to chaos for flow over an elliptical oscillating airfoil at low Reynolds number is through quasi-periodicity. We identified that there exists a limit cycle even if the airfoil starts its motion from different initial conditions, and these are physical initial conditions. And then we talked about the reduced order models which were developed for lift of the pitching and plunging and flapping airfoils. As far as the hydrodynamics is concerned, for the flexible fish, we established that upstream fish remains independent of the phase speed of the rear fish. Then we also observed the inverse drafting for reduced muscle activity for the rear fish. That is basically a contribution. And then we talked about the certain range of frequencies, ratio and distance between which where that drafting can be observed with reduced muscle activity of the rear fish. And then we talked about the symmetry or the nature of the hydrodynamic modes. We found out that those modes follow the same symmetry principles which are true for blunt bodies. So this is important for finding out similarity between all the natural flows. As far as suggestions for the future work are concerned, nonlinear analysis can be more insightful if we are to perform the three-dimensional or the finite aspect ratio based flows. Why? Because they take so much time. Three-dimensional flows, the simulation of three-dimensional flows takes so much time, and by the way, if you want to perform the nonlinear analysis, it may take even weeks, because we need to get a long time history for that. More physical understanding can be obtained through incorporating real geometry and kinematics, which also involves banking of the wings. We can also involve the passive flexibility into the system. And then we need to see the contribution, actual contribution, that what percentage of lift is being produced by which mode. So that is still to be done. We have talked about the passive flow control in tandem configuration. We can go for the active flow control as well. So this study helps us to look at the dynamics of the system. And then, because we are talking about the fifth swimming, which is an open channel flow, so free surface and shear layer effects also need to be incorporated in the numerical models. So with this, I end my presentation. Thank you for your patience.